Hey guys, welcome to Physics Today. Thanks for tuning in to Dr. Neutron Radio Hour. We've got a good show for you today, so grab your calculators and get your pencils out. I want to start today by saying that my son is good. He had a tummy ache and we had to go to the doctor, and he does not have COVID, so that's a relief. Sorry I couldn't be there today, but I think it's going to be an epic video. So we are starting on chapter 11 today, and we've got about 2 to 3 more chapters left, probably 2 before we wrap this whole thing up for the summer. So we've only got a few more days, so let's get started with chapter 11. All right. So, chapter 11 is all about using energy. How do we use energy? What do we use it for? And what are the different types of energy that are available? And we're going to be talking a lot about how human beings use energy in our own bodies. So, when you go to lift something, besides just doing the mechanical work where you're adding potential energy, your body also has to metabolize energy. So you have to convert energy from food you eat into actual chemicals that will make you move your muscles. And that is a somewhat inefficient process, and we're limited by a number of things. We're going to look at how, when you use energy, how much of it is actually useful energy and how much of it is wasted. Some things that we can do, we can make things more efficient, but at the end of the day, we're limited by the laws of nature. Some things can't actually be made more efficient, but some things can. All right. So we're going to learn about practical energy transformations and limits, and what are the limits on efficiency. So when a kangaroo jumps, they convert their food into mechanical energy, but a lot of that energy is lost due to heat. So when you jump up in the air, you have to add energy into the system in order to gain potential energy. But when your muscles work, you lose a lot of energy due to heat. All of the food that we have, all the energy that we have, comes from the chemical food that we eat. And we're going to learn how to calculate how much energy your body requires to complete a range of tasks. For example, jogging down the street, riding a bike, or walking a flight of stairs. So we are not perfect machines, just like blue whales. So we lose energy all of the time. And once that energy is lost from our bodies, it's not actually destroyed. The energy is still around, but it is not in a useful form. So once you turn the chemical energy in your body into useful work, you lose some of that energy to heat, and it goes into the environment, and you can't recover that energy. Same thing when you burn gasoline. You can take some of that energy and convert it to useful mechanical energy, but a lot of the energy is gone and just lost into the environment. Okay. Now, when we burn a kettle, some of that energy is transferred from gas into producing heat, and some of it goes into boiling water. But a lot of the energy is lost into the room. Now, you can have different types of stoves, but you can think about it like this. If you, say, burn energy at a gasoline, at a natural gas plant, and produce electricity, if you have an electric stove, you're going to be taking that energy and first of all, you're going to convert it from natural gas into electrical energy. So you're going to create heat, you're going to boil water, which is also a very inefficient process. Then that water is going, the steam is going to turn a turbine and it's going to produce electricity. And now you've got to get that electricity from wherever it's being generated to where you actually want to use it, which hopefully is not too far away because you lose a lot of that energy just in the act of transmission. So when you're transmitting energy from the power plant to your house, you lose over 50% of it. Now, if you again turn that back into heat, you're only gaining a little bit back of it. So that's why if you can get natural gas in your house for your stove, it's a much more efficient process, which is why most water heaters are actually gas because then you've got your primary energy source right there. You're burning the natural gas in your house. You don't have to convert it into electricity, send it down a power line, and then turn it back into heat. So all those things are going to cost you. So if you can burn the gas in your house and heat the water right there, that is a much more efficient process, which is one reason why natural gas is so much better because you can transport it to your house and then burn it right there. And you can actually use most of that energy to do something useful. So heating your house, heating your water, cooking with it. If you have a gas stove, it's a much more uh, efficient process. And so your carbon footprint is going to be much smaller than if you burn coal at a power plant, send it hundreds of miles, and then convert it back into heat. All right. So we're going to learn that heat is energy transferred due to the difference in temperature between two objects. So I always tell my wife, I say, there's no such thing as temperature, right? It's really just the transfer of energy from one thing to another. But you could say there really is temperature because things could be at two different temperatures. So temperature is a thing, but it might not actually be what you think it is. All right. So, um, a heat engine is a device such as a geothermal power plant that transfers thermal energy into useful work. So, if you can collect heat from underground, maybe a lava or magma deep underground, and then you can convert that into useful mechanical energy. You can basically boil water and generate electricity. But we're going to learn how to calculate the maximum efficiency during this process. In the last chapter, we focused on mechanical energy. But in this chapter, we're going to focus on thermal energy, chemical energy, and energy transfers in the form of heat. So if you have two things at different temperatures, energy will pass from the hotter object into the colder object in the form of heat. During that process, we can actually perform work. Now, if you have a system that is completely isolated, then we say the total energy of that system is conserved. If it's not conserved, then there's heat exchange between your system and the environment. So if you look at the picture right here, we've got some system where we have kinetic, potential, and chemical energy, and this produces thermal energy. But if energy is transferred to or from the system in the form as work and heat, then this is not a conservative system. So in any real type of engine, you're going to lose energy to the environment. There's really no such thing as uh, an isolated system. All right. Let's just look at this example. Christina throws a javelin into the air. As she propels it forward from rest, she does 270 joules of work on it. Now, when it gets to the highest point, its gravitational potential energy has increased by 70 joules. So that means the total energy has stayed the same in our system, but now some of it has gone into potential energy. That means there's less kinetic energy than when she started, and now some of it is in the form of potential energy. So, what is the javelin's kinetic energy at this point? Well, we took kinetic energy and we converted it into potential. So, here's our javelin thrower. She throws it up like this. It's going up. When it reaches the top, then we lost 70 joules of kinetic energy, which became potential energy. So we subtract 70 joules from the total, which gives us 200 joules. So the kinetic energy is just 200 joules. And in this system, there was no energy loss due to wind resistance or anything like that. All right. What is the typical efficiency of the human body? Humans are somewhat inefficient, so a lot of the energy that we eat does not go into doing anything useful in terms of moving. Now, that's not to say it's not doing something useful because it takes energy to run your body. But really, you only end up using 25% of the energy that you put into your body to do something useful. So if I'm carrying a heavy box or walking up the stairs, only 25% of that energy would go into uh, mechanical motion. So increasing my potential energy. The rest of it goes into the form of heat. So getting my muscles to move. I'm going to start sweating. I'm going to be really hot. I'm giving off tons of energy to the environment around me. And I'm only going to be able to use 25% of that for something actually useful. All right. So machine uses 1,000 joules of electrical energy to raise a heavy mass, increasing its potential energy by 300 joules. What is the efficiency of this process? Now, if we could convert 100 joules of the electrical energy into, or sorry, 1,000 joules into increasing our potential energy by 1,000 joules, then it would be 100% efficient, but it's much less than that. So what we do is we take the 300 joules of actually doing something useful, we divide that by 100, and it gives us 30%. So that's how we define what our efficiency is. We take the useful work that was actually done, so increasing potential, and we divide that by the total energy it took to use them. So, uh, in in an electric motor, you probably noticed that when you even your computer when you turn it on, if you're playing a video game or doing something that takes a lot of energy, your computer gets hot. Well, that's all energy that's being radiated. Especially if you play a video game, your fan's going to be going. It's going to be blowing lots of energy into the environment. Same thing with an electric motor. That motor is going to get really, really hot. You're going to lose some of that energy. So even electric motors are not 100% efficient. But we're going to get to that later when we start talking about cars. So one of the things that we've been talking about in class is electric cars. So one of the things that we questioned was, are electric cars really good for the environment? Because we have to consider the total cost of the car, not just what you get into it. Okay. So that means how much does it cost to manufacture the car versus how much energy you're going to save when you drive the car. Now, electric cars are much more efficient than gasoline cars, but it also depends on how are you making the electricity for your electric car. Are you burning coal to power your electric car? Because maybe that's not really that efficient. Now, if you're using solar or wind, then you're not producing any air pollution to run your solar power car. And so you'll be saving energy. All right. So we're going to look at the cost, the total cost of a car versus how long it takes to get that energy back. But let's start with how electric cars work, and let's look at their efficiency compared to just, say, a gasoline powered car. All right. Well, first of all, the common method of creating an electric potential difference is a battery. That just means that a common way to store energy is in a battery. We can take mechanical energy, convert it into electrical energy, and store it in a battery and use it at a much later time. So that's what's amazing about batteries is you could take that energy from water flowing in a hydroelectric dam and keep it for days or even years in a battery. But there is a cost to using a battery that's not totally free. So if you make a battery, it takes certain elements like lithium, cobalt, rare earth elements. We have to get all those things from different places. But let's just talk about the overall efficiency for now. So a battery uses a chemical process to maintain a constant potential difference between the anodes. That just means that as you change that mechanical energy from your hydroelectric dam and you convert it into electrical energy, you can uh, create a chemical process that stores that energy for some time until later. So you charge your battery, you um, cause a chemical reaction to occur so that when you hook up a load to it, you can get that energy back and create electricity. Once that chemical process starts, you get electricity, which you can do things like turn the motor in your car so you can power your car. So you can store energy in a chemical process and then use it to power your electric car. Okay. So uh, in a Tesla, which is actually faster than a Lamborghini off the starting line because electric motors have a lot more torque, unless you get the insane package for the Lamborghini, which is only an extra $30,000. But, if you're buying the Lamborghini Aventador for $450,000, what's another $30,000? I mean, if you want to be faster than the Tesla. But so we can store energy in our Tesla, either from a coal plant or a hydroelectric dam or windmills or solar, and we could use it at some time later. Now, let's compare that to a normal automobile. Okay, so a Tesla sports car, it has a 53 kilowatt hour lithium ion battery that's charged to 80% of its capacity and discharged to 20% of its capacity. That just means to keep the battery in operation at peak operational performance, you don't want to charge it all the way, and you also don't want to discharge it all the way. So you can go to 80%. If you go to too much, it starts to lose its capacity. And a Tesla battery is probably not cheap. You can get a Tesla battery to store energy from your house and use it at nighttime. Now, typical gasoline powered car carries 50 liters of gasoline, which has an energy content of 34.8 megajoules per liter. Now, we compare that to a battery, which is in 53 kilowatt hours. So those are two different units. And so we need to convert these both into energy so we can compare them. So I'm going to show you how to change kilowatt hours into joules because that's what we're one of the things that we're after. And then we're going to see which one is more efficient. All right. So, how does the available energy in the Tesla sports car compare with the energy carried by a gasoline powered car? All right, let's convert our energy stored in the battery. Right now, a watt is a joule per second. Okay, so we need to convert watts into joules, and um, so when you get a battery, it's usually in kilowatt hours. So it's a funny way of basically saying, telling you how much energy you have, and this is how you convert it. So first of all, between we can only use 60% of the battery's capacity. So we multiply that by 53 kilowatt hours. Right, so let's go down here. All right, so this 60%, that's the capacity of the battery that we can use. And here is the energy in our battery. Okay, but this is really saying, well, how many joules are in our battery? We can figure that out by saying, all right, a kilowatt is 1,000 watts, which is 1,000 watts divided by 1 kilowatt. This is our conversion. And then we're saying watts is joules per second. So we've got it in hours, and so we need to convert hours into seconds. And in 1 hour, there are 3,600 seconds per hour. So we multiply that uh, by our kilowatt hours, and then that's going to give us joules. Right? A watt, remember, a 1 watt is equal to 1 joule. I lost my mouse per second. All right, can't see that. So there we go. My mouse is back. So 1 watt is equal to 1 joule per second. So our seconds are going to cancel out our our seconds are going to cancel, and it's going to end up just leaving us joules. So this translates, once we do all the algebra, into 114 megajoules. All right, so let me clear all this stuff. All right, so now we've got 114 megajoules. We need to know how much energy is in our gasoline powered car. How much are we storing? All right. So in a typical gasoline tank, you can store about 50 liters. So we multiply that by the number of megajoules per liter. So 34.8 megajoules per liter. That gives us 1,740 megajoules, which seems like a lot, right? You're like, wow, that's a way more than an electric motor, but actually 15 times more. However, a typical gasoline powered car is only 20% efficient, while it's 90% for a battery powered car. That means that 80% of the energy stored in that gasoline is lost due just to heat and friction, other sources. It's gone. It goes into the environment. That energy just turns into heat, heating up the air around your car. Your car takes a lot of cooling, needs a lot of cooling. So all that energy just gets dissipated into the air around you, and it's not recoverable anymore. All right. So that means that if our electric car is 90% efficient, 90% of 114 megajoules is 103 megajoules. Now, a gasoline car is only 20% efficient, but we've got a lot more energy to work with. So 20% of 1,740 megajoules is 348 megajoules. So what does this mean? It means that you can drive a gasoline powered car a lot farther than you can an electric car. It's got capacity to travel for a very long distance. So if you're going out on the open road, you're going to need some gasoline if you want to travel long distances, unless you can get to a charging station. If there were charging stations along the way, then you could charge up your electrical car and it wouldn't be a problem. But Teslas require special charging stations. And if you don't have a special charging station, it can take many hours to actually charge your car. They do have high speed charging stations, but those are very specialized, and you might not find those between here and, say, Kansas City. kind of sketchy. So, what does that mean? Well, uh, driving around the city is great for an electric car, but if you're going to be going long distance, you might need gas powered. So, realistically, we may not eliminate gasoline completely, but because it is useful for traveling long distances. However, uh, if we had higher capacity batteries, it wouldn't be an issue. But this begs the question, uh, is an electric car truly more efficient than a gasoline powered car in terms of its total footprint? That means manufacturing, driving the car, your energy content, because you still have to get your energy from somewhere. And let me just also say that it's not all doom and gloom. Even though um, there are problems with alternative energy. It's not perfect. These are things that we could overcome. So going forward, um, it does make sense to use alternative energy because you're using much less energy overall, and I'm going to show you that in a second. But the point is that you can do something about it. Using electric cars is better for the environment if you can, especially if you can get that from, say, solar or wind energy. Then you're really reducing your carbon footprint. Let's take a look at this article from the Sierra Club. So, not too long ago, Argonne National Labs did a study. They wanted to know how much basically gasoline does it take to produce a typical automobile, and how, including a normal car and a Prius. We can compare those two numbers, and so they looked at all the different pieces, the components, and they converted it into gallons of gasoline. And so for a basic 3,000 pound cars, they found it takes about 260 gallons of gasoline to make that car. Okay, now a Prius takes more energy, okay, because you've got to deal with the battery. The battery does take a lot more energy. And so, for an equivalent hybrid car, it takes 325 gallons of gasoline to produce that. Okay. So, that is the carbon that you're putting into the atmosphere. Okay. Now, depending on what kind of car you are currently driving, you might want to know, am I going to be helping the environment if I say replace my car and drive a hybrid, right? Because that's a good question. We want to know, are we saving energy, or should I stick with the car that I have because it's already been produced, so I can save that production cost, right, and just keep driving the clunker that I have? What's a better deal? So let's talk about that again. Prius takes 325 gallons to make, and a normal car takes about 260 gallons. So Prius is more expensive in terms of gallons of gasoline used. But let's say your normal car gets 32 miles per gallon, or let's say you drive my car, which gets about 25 miles per gallon. Let's do a calculation. All right. So let's say we drive 13,000 miles and our car gets 25 miles per gallon. Okay. That means we get our calculator. That on average, we're going to use 520 gallons of gasoline per year. So that's enough to make 2 Priuses. Wow. I need to get a new car. Oh my God. Now let's say your Prius gets about 50 miles per gallon. So then we're going to say, all right, 13,000 and we are going to get 50 miles per gallon. All right, so 1,313,000 divided by 50 miles per gallon. That is 260 gallons of gasoline. That's for 1 year. Wow. All right, so let's do a little calculation now. And let's say, so 520 gallons from a matrix minus 260 gallons. That's 260 gallons. All right. So that means in less than 1 year, the extra, so to make a Prius, it's 325 gallons minus 260 gallons for a normal car. That leaves us 85 gallons. Wow. That means that in a few months, you've already saved that extra energy for your Prius. Wow. So, so what can we learn from this? That means that if your car gets 25 miles per gallon in 2 months, you've saved the energy that it would take. You've saved the extra energy it would take to make a Prius. Okay, and in 8 months, you've used as much energy as it would take to make a new Prius in your car that gets 25 miles per gallon. So the moral of the story is that electric cars really do save a lot of energy, even if you look at the whole life cycle of the car. If you're talking about a car that gets less than 20 miles per gallon, you can easily make that energy back in the first year. So your energy savings are huge compared to a car that gets 25 or less miles per gallon, which a lot of cars are not really doing much better than that. So the moral of the story is electric cars are good for the environment. But now you might say, Dr. Wisby, what about the elements that we use to make those? What about lithium and cobalt? Well, I'm glad you asked. As it turns out, a lot of the modern electronics that we use do take lithium and cobalt, and unfortunately, these resources can only be found in a few places on Earth. One of those is the Democratic Republic of Congo. Now, pretty much every kind of electronic needs these for batteries, which means we are getting cobalt, lithium, other elements that are hard to get from these countries that oftentimes use what's called artisanal small mining. Unfortunately, this is often done with child labor. Little kids are doing this. It's not just for it's not just for electric cars, it's for all electronics. The problem is, uh, if you want to try and get rid of this, not use child labor, it's very hard to do because once the cobalt gets into the market, it gets mixed up with all the other cobalt. And so you can't really say, where is this coming from? Is this coming from a mine that's using children or not? But let's talk about child labor. It's a huge problem, but in, especially in poor developing countries, sometimes these people literally have no other income. It's the only source of revenue that their families have. And if they don't get that money, they could starve. So, what could we do? We don't want to have children mining these minerals, and we also don't want people to starve to death. There are many problems, but I guess I'll close with just saying that uh, I'll talk about two people that I think have really good ideas. One of those is Pope Francis. Pope Francis says that climate change is a huge threat, especially to poorer people. Poorer people are going to suffer the most. Um, they are the ones that are least able to afford to adapt, and they often live in places that are most susceptible to the ravages of climate change. We're already starting to see this with indigenous people. Um, those people are not able to move, are not able to protect themselves. So, climate change is going to have a huge impact on poor people. And another important person, Dr. James Goodall, says that we can't really save the environment unless we end poverty. So, if we want to end child labor, the solution is we need to end poverty. So, what am I trying to say? Is that electric cars are good for the environment. They're not perfect. Saving the environment is not just about driving electric cars or recycling your cans. There's a bigger problem. We all live on this planet together. If we want to save the environment and make it a place that we can live for many, many years to come, we're going to have to tackle the issue of poverty. Unless we can do something about poverty, then we're headed down a path that is probably not sustainable long term. A good example of that is the coronavirus. We have come to a place in the world, and this is something Dr. James Goodall talk a lot about, where humans and people live in close proximity to each other. Often these people have to hunt for animals in the forest and eat things that are really probably better not eaten because they have no other option. So a lot of people are eating this food that's unsafe and uh, and having to mine things because they have no other income. So if we want to solve these problems, we have to do something about poverty. Unless we solve poverty, we're not going to save the environment. Because people are in close proximity with animals, we could see something like the coronavirus happen again. It's not a question of when, it's not a question of if, it's really a question of N, of when. When will it happen again? Wow, that was heavy. But on a lighter note, I truly believe, as does Dr. Jane Goodall, and if you don't know who she is, you should spend some time looking it up. Uh, there's still hope. It's not too late, but it's up to younger people. Younger people, I believe, are the ones that can make a difference. That means you guys, people in my class, maybe even your kids, are the ones that can change the world. So I hope you have a good night. I look forward to seeing you tomorrow, and we will continue with our final week of Physics 1. Thanks for watching. Have a great night.
Thank you, like and subscribe down below.